In this video, I'm going to show you how to do implicit differentiation and derivatives of inverse function. Up until now, you've probably been doing explicit differentiation, which is just the normal kind of differentiation. Explicit differentiation is when you just have a normal y equals function or y equals some x expression, so it is a function explicitly in terms of x. And you probably already know how to take the derivative of something like this. You just use the power rule, differentiate with respect to x, and your derivative or dy dx would just be 2x. But what if your function is not written as y equals some x expression? Well, then you have to use something called implicit differentiation. So if your function is not written as y equals but is written implicitly as a function of x, is x squared plus y squared equals another term or a number 16. You can't do the normal explicit differentiation, so you have to use implicit differentiation, which is a special kind of a chain rule. So let me show you the main steps for implicit differentiation. Okay, so these are the two main steps for implicit differentiation. The first step is that you need to differentiate both sides with respect to x. So take the derivative in terms of x, but the difference is that you need to differentiate a term that has a y in it. You will need to attach a dy dx to the term, multiply the term by dy dx for instance that you wanted to differentiate with respect to x. A 2y squared can be solved by using power rule. To differentiate normally, the 2y squared would give you a derivative of 4y, but because it has a y in it, you will need to tack on or multiply a dy dx at the end. Why do you do this? Well, the answer is that it is a form of the chain rule. Because there is an outside function, the 2y squared, that you use the power rule for, the y contains some x expression which is composed, so you will need to multiply by an inside derivative to take care of that inside expression, and the inside derivation is dy dx, so you can think of that way. The second step is then to just solve for dy dx. That means get dy dx alone on one side, so that your expression looks like a dy dx equals something. So let me show you how it works. Okay, what if you have a function like this that doesn't start with y equals? It is written implicitly in terms of x. The first step is just to differentiate both sides with respect to x. So for the first term, x squared, the derivative of that would be 2x using the power rule. Move on to the second term, y squared is take the derivative using the power rule. The derivative of y squared is 2y, but because there is a y term and contains some expression, you need to multiply this term by dy dx. This is the difference between implicit and explicit differentiation. Moving on, you need to differentiate both sides from the equation. But if we're looking at the right side of the but if we are looking at the right hand side, since we have a constant number 36, the derivative of that will be 0, at it always is for a constant, so we will just write 0. Then proceed to the second step, which is the dy dx, get it alone. So if there are ever any parentheses you'd want to distribute or multiply out to get rid of them, but there are none in this case. We just need to get them that they have dy dx alone on one side. You need to subtract out any terms that don't have dy dx. So we will subtract the 2x from both sides, and we have 2y and dy dx equals negative 2. In order to get dy dx alone on the left hand side, we have to divide both sides by 2y, and those cancels, and we're left with just dy dx on the left hand side, which is what we wanted. Equals negative 2x over 2y, which can be simplified by dividing 2's as negative x over y, which can't be simplified any further. We have only dy dx alone on the left hand side, so we're done. This is our final answer. dy dx equals negative x over y. Today, we're going to go over the derivatives of trigonometric functions, and there are 6 of them, so you need to know all of them. Let's start with the first one. The derivative of sine x, cosine x, and the derivative of cosine x is sine x. Now look at the pattern from what I have written. The derivative of tangent is secant squared, and the derivative of cotangent, the cofunction of tangent, is cosecant squared. But with a negative sign, the derivative of secant, that is equal to secant x, tangent x, and derivative of cosecant x is negative cosecant x, cotangent x. So notice that the derivatives for every cofunctions, particularly those who starts with a c, they all have a negative sign. And notice that the similarity between tan and cotan, the derivatives of tangent is secant and cosecant, are similar. The derivative of secant is secant tan, and the derivative of cosecant, negative cosecant, and the derivative of cosecant is negative cosecant, so there are some similarities. And now let's go ahead and work on some example. So let's find the derivative of this expression 5 sine x minus 4 tan x. It's going to be the 5 times the derivative of sine x minus 4 times 5 to the derivative of tangent x. Now, know that the derivative of cosine is positive cosine, and the derivative of tangent is secant squared. So the answer is cosine x minus 4 secant squared x. Now, let's work on another similar example. If we want to find the derivative of 8 secant x minus 5 cosine x. So based on the last example, this is equal to 8 times the derivative of secant x minus 5 times the derivative of cosine x. How the derivative of secant, it's going to be the secant, and tangent and the derivative of cosine is a negative sign. So the final answer is going to be 8 secant x tangent x plus.